Not much information, right? If it's that little information, that should be easy to memorize or easy to remember, shouldn't it? I think. But it's like, somebody asked me, about, it was something we discussed on day one. What did we discuss on day one? Scientific method. It was something about the scientific method. Oh, yeah. Yeah, I asked about empirical equations, right? And I was surprised. This morning, the empirical equation came up again. So I asked people about empirical equations, but a lot of people didn't know what empirical equations were, still didn't know what empirical equations are, which surprised me because it's different. It's like, would you want to go back to kindergarten to study? No, you wouldn't, because, that stuff is so boring and easy, and it would just be a waste of time, wouldn't it? Well, that's the way it is in class, because the stuff on day one, by the time the final comes by, it should be like the stuff from kindergarten. It should be kind of boring, easy, because by the time the final comes around, you've seen it so many times. Problem is that a lot of people, they don't do anything, they don't learn anything new until, right before the final, and then go back and review it, and it's all long gone memories. So, by now I was thinking empirical equation should be like automatic. There should be no hesitation. What is an empirical equation? Yeah, that comes from, right, and so some people are saying it came from theory this morning, and I thought, wow, that's really, don't want to keep that misconception all the way to the final, otherwise it's going to be in trouble. So that came up. And so you want to go back through, and we're going to talk about empirical equations today. Anyway, so some of this stuff we need to know, like the kilogram, you don't really need to know. What is it made out of? It's made out of platinum iridium. Is that not all that important? No, but maybe it makes sense because it's two of the most dense elements on the periodic table. So they can make it small rather than, if they pick something that wasn't as dense, it'd be pretty big. Right? So this would be a lot easier to store. Since it is so dense, that is, it weighs a lot. This is kept in a bell jar like this. Do you see that little thing there? What do you think that little valve is made for? All right. Bell jars do they have? 1, 2, 3. Usually a little valve like that is made for sucking the air out and then backfilling it. You don't want to keep the vacuum in here because the air is going to leak in. So usually you suck out the air and then backfill it with an inert gas, like what? Something that's not reactive. Like nitrogen. Nitrogen would be cheap, but the problem with nitrogen is that nitrogen, they usually try to use a heavier gas. Not like helium. Helium's pretty light. In fact, helium is probably the least dense element on the periodic table. And the most dense would be osmium and iridium. Least dense would be like helium. But they use something like argon. Argon's a good blanket gas. You keep this under argon. Even though, platinum and iridium is really resistant to corrosion or reaction, there's still potential for a little bit of corrosion to occur, so you want to keep this protected. They control the atmosphere. This is called modified atmosphere. All right, so that's a kilogram. The kilogram, if you wanted to know if you had a kilogram or not, you'd have to compare it to this. And then a gram is 1/1000th of that. A meter is a little bit easier, maybe. A meter is the length of the path traveled by light in a vacuum in this time frame. So that would be a meter. But that's hard to measure also because of the vacuum. You know, is it easy to suck out all the air out of a jar like that? No. In fact, if you were to suck out all the air out of a jar like this, you'd have to worry about implosion. You know, is that jar strong enough to handle it? Because if we suck out all the air out of here, then there's no pressure inside here, but there's pressure outside. Do you know what air pressure is, roughly? Air pressure is 15 pounds per square inch. So there'd be 15 pounds per square inch of air pressure pushing on the outside. If there's nothing on the inside, this could be like a submarine. You know, a submarine would just be crushed by the pressure. Or the glass can be crushed by the pressure. And so typically when we do vacuum work, we have to use stronger stuff. Not usually glass, although we do a lot, but not very high vacuum. If you're doing very high vacuum stuff, you don't want to use glass because glass can implode. And so rather than using glass, you still have it. Use stuff like this. This is all heavy walled stainless steel, so you don't have to worry about implosion, you know, by sucking out all the air out of there. And then this one is made for doing studies, so there are a whole bunch of windows here, very thick, like submarine glass, and there are a whole bunch of leads going inside there, so they can do it. This one looks like they're trying to grow crystals inside there, probably. And so if you're growing crystals, you want the environment in here very clean. If you want it very clean, then you suck out all the air and keep it as a vacuum. Even if you backfill this with argon, it depends on how pure the argon is. Is it high purity or low purity? You know, how pure is it? And so we worry about that as well. But this is what we call UHV, or ultra high vacuum. UHV or ultra high vacuum still, it does not approach a perfect vacuum. It doesn't because, you know, you have all these joints here and gases can leak in. Not only that, helium can leak through the walls of the stainless steel, cause a vacuum leak there. So you spend most of your time getting rid of the vacuum leaks that pop up around here. But even then, when everything's pulling optimally, the pumps and whatever else you have on there, you still can't achieve the very highest vacuum. So some people had an idea, you know, they wanted to grow or synthesize very high purity, I think it was silicon or germanium, semiconductor wafers, you know, crystals. And so they were thinking, well, you know, they could do that on Earth using vacuums like this, but you can't generate as good of a vacuum on Earth as you could on space. And in fact, the vacuum of space might be just what's needed to grow the purest, because you know, when you're growing crystals, you know, any little contaminant will screw up the order of the crystals and contaminate it and lead to impurities. And so one of the scientists had an idea. They're going to grow crystals on the shuttle. And so what they did was they designed an arm that deployed out of the bay of the shuttle, and then they had all their crystal growing apparatus there on this. And so they went to grow crystals out there rather than on Earth in a clean room, in which all the dust is, or most of the dust is removed. A vacuum like this created. But when they got the crystals back on Earth to analyze them, they turned out to be even more contaminated than the ones they could grow in labs. Do you know why they're more contaminated? Because of the tiles. You know, the tiles on the space shuttle are made out of this material called aerogels. Have you heard of aerogels? Aerogels are ceramics that are less dense than air. In other words, they're lighter than air. You know, and it's like, they're really weird. They float on water and they're less dense than air, so they have buoyancy in air. It's really strange things, but they're excellent insulators, so that's why they use them as tiles, and they don't weigh much. Well, anyway, it turns out that those have high surface area, so they absorb a lot of air and contaminants. And so when the space shuttle goes up in space, it takes a long time for all the contaminants to degas off the surface. And so when they did this experiment, the space shuttle was degassing a whole bunch of contaminants, which contaminated their experiment, which made the crystals very expensive, but not very good. So, same thing. Well, that was a talk I went to, and also during this talk, the engineer, this is an engineer who was working in Silicon Valley at the time, talked about one of the challenges at their plant. You know, they're growing. They're making semiconductors, but it turns out like a single piece of dust, is huge compared to atoms. And so if a single piece of dust got into their chip, then it would be a reject. That is, they can use it. And so if small quantities of impurities get into their chips, it screws everything up. And so they have very, very clean laboratories in which the air is continuously filtered. You have to wear special clothes, et cetera, et cetera. But they were still getting a certain defect rate. That is, they had to throw away a certain percentage of the chips because they just didn't work. They were defective. And so what they did was they made the room even cleaner and cleaner and cleaner. So the percentage of impurities kept decreasing as the room got cleaner and cleaner. The impurities were more effectively removed, but the defect rate stayed the same. And so the contaminants decreased, defects stayed the same. It didn't make sense. It didn't make sense because if the room gets cleaner, then there should be fewer defects. They won't get incorporated in the crystal structure. So the moral of his story was, and this was a talk at UCSB. The moral of his story was, you should keep an open mind towards education, because you might think, all these little trivial details are worthless. I'm never going to use it, so why even bother memorizing some stupid little thing here and there? But he said, it's because he was open-minded. It was because he was open to learning new things, even though he didn't know what might apply or what might not apply. He was able to figure out what the problem was. And the problem was the defect rate should be going hand in hand with the decrease in contamination. We should see a decrease in the defect rate, right? But he said that he went to a talk. The talk was about, space, and something about radiation. And so during the talk, the talker was talking about cosmic radiation and cosmic radiation bombardment on Earth. And then it came to him that maybe the reason why the defect rate is staying constant is it's not because of the cleanliness of the room, it's because of cosmic radiation bombardment. A cosmic ray hits it, causes the crystal, a defect in the crystal, which means that the chip doesn't work. And so what he did was he ended up shielding the laboratory from cosmic radiation. You can shield it with metal. And after he shielded the lab, that was the problem. The problem was cosmic radiation was the cause of this. But it would the thought he was the person in charge. But none of his team or he would have ever thought of that unless he went to that talk, which was just wasn't directly related to him. He didn't deal with astrophysics or whatever it was. So you never know. Never know where you end up. It's like you would think like my lab mate. He invested all this time into getting a PhD in chemistry, and then what he did after he graduated? He went to work for he went to work for this company which was bought out by HP, but he went to work doing data data transfer. Can you believe that? It was nothing related to chemistry at all. And then you ask him, did you think it was a waste of time, getting your PhD in chemistry, and here you're working with computers and data, big data? He said, no, that's actually what led to working in big data, was working with all these files in chemistry. And so, even though a lot of this stuff might not seem that significant or important, you should try to make a little effort to learn it, like empirical equations, whatever else we're doing. And it'll become easy. It'll be like kindergarten after you review it enough times. Initially, the stuff is hard. Initially, the math, in elementary school can be quite hard and challenging. But after you see it enough times, it's pretty easy. The same thing with this chemistry stuff. Hopefully, by the time the final comes, all this early stuff that we're talking about now is easy. All right, let's continue on with the chapter 3 here. We're going to finish up chapter 3 today. So we have the metric prefixes. What metric prefixes do you need to know? That's something we talked about the other day. Let's start off with the biggest, and then work our way down to the smallest. What's the biggest metric prefix?
Tera.
Tera? Mm-hmm. Tera, and then?
Giga, mega, kilo, centi, milli, micro, nano.
Now, pico. Usually we stop at pico, but a lot of people go to femto. Femto is the next one smaller. The reason femto is important is because of femtosecond lasers. There's lasers that give a pulse of light in femtoseconds long. It's incredibly fast. And there they can corrode things that are incredibly fast. You need something incredibly fast to measure something incredibly fast. And so people are trying to develop faster and faster lasers. It used to be picosecond lasers were the state of the art, but now it's femtosecond. Maybe it's even faster now. All right, so we need to know those prefixes to do these types of conversions. Like how many grams are there in 0.711 kilograms? Can you do this one in your head? No? So we moved it, the kilos, 3 decimal places over 1,000. And so we move it 3 places to the right or 3 places to the left. So how many grams? So a gram is smaller, so we got to move it to the right. So it's 711 grams. Would be it. So let's take a look. Or we could use dimensional analysis. Here they're going to use dimensional analysis. Using dimensional analysis, we need to cancel out kilograms. And so the relationship is there's 1,000 grams in a kilo. Kilo means 1,000. 1,000 grams. Kilograms cancel, that leaves us grams. So we essentially move it 3 places over by 711 grams. How many sig figs do we have here? Sig fig. 3. 1. 1. Would you guys agree? 3, 1, 1. Well, this is why we need to know about exact numbers versus inexact numbers. Inexact numbers, another name for inexact numbers is measurements. All measurements are inexact. No matter how precise or how careful you are, there's always a little bit of uncertainty. You can measure something and you say, I measured it exactly, but another person could measure and they could say or claim they measured exactly, and your 2 numbers might not match, even using the same thing. And so this one, 7.711 kilograms, would you say that's exact, or is that more typical of a measurement? It's more typical of a measurement, so I'd say that's 3 sig figs, so you're right. I wouldn't call it infinite. But what about this? Is this exact, or this is exact? Because would you say this, there's approximately 1,000 grams plus or minus a few per kilogram, or exactly 1,000 grams there. Exactly 1,000 grams. And so that means this is infinite, that's infinite. So 3 sig figs, infinite, infinite means I have 3 sig figs in my final answer, so I gotta drop to 0. This one I can do in my head. I could do the last one in my head because I've done lots of those. But this one, I'd probably sit down and figure out using dimensional analysis. Dimensional analysis, I mentioned, is the main method of solving problems in chemistry. There are a couple of other methods which we'll talk about, but this is the main. And so this is 5.25 times 10 to the 5th milligrams equals how many kilograms? And so dimensional analysis, we just start off. I don't know how to get there necessarily, but we'll try. 5.25 times 10 to the 5th milligrams. What I'll try to do is I'll try to figure out some relationship that takes me from milligrams to something else. And so I want to go from milligrams to something else. Anything. That way milligrams can cancel. And so what do you know? What can you relate milligrams to? Grams. And so the relationship is there's 1,000 milligrams in 1 gram. Or 1 gram is 1,000 milligrams, or 1 milligram is 1/1,000 of a gram. So, all those. And so we can go from milligrams to grams, and then we need something that gets rid of grams. Preferably, it would be nice to go from grams to kilograms, which we can do, because there are 1,000 grams for every kilogram. And so these are conversions that we can use. So the grams cancel out, and these are some kilograms. And so what would the answer be? Well, this would be 1,000 10 to the third, 1,000 10 to the third. So 10 to the third times 10 to the third is 10 to the sixth. Then bring that to the numerator, it's 10 to the minus 6. And 10 to the minus 6 times 10 to the minus 5, 10 to the positive 5 would be 5.25 times 10 to the minus 1. And 5 minus 6 to the minus 1 milligrams. This is better written in decimal because it takes up less space. So this would be 0.525 kilograms. All right, this would be how many sig figs? Does this look like a measurement or an exact number? That looks like a measurement, so this would be how many sig figs? 3. How about these? Infinite? Exactly. Sometimes I'll write the 1, sometimes I won't. Like here I wrote the 1, sometimes I'll leave it off. But this is one thing. This is an example of a 2-step problem. I never keep track of the steps. 2-step, 3-step, it doesn't matter. I'll just string on as many as needed. It might be 1, it might be 10. A fruit drink is sold in bottles that contain 1,892 milliliters. Express the volume in cubic centimeters and in liters. Well, we know the milliliter. Milliliter is abbreviated little m, big L, milliliter. 1 milliliter is how many cubic centimeters? 1? 5? 1,000? Well, it turns out a milliliter and a cubic centimeter are the same thing. And so they're the same by definition. That's what this 3 lines mean. 1 milliliter is defined as 1 cubic centimeter. And so, excuse me, if I have 1,892 milliliters, it's the same thing as 1,892 cubic centimeters, same thing. But it's not in terms of liters. In terms of liters, then we need this. How many milliliters are there in a liter? Milliliter is small, liter is big. Millis 10 to the minus 3, so there's going to be 1,000 milliliters per liter. So if we take 1892 divided by 1,000, we're going to get 1.892 liters. So milliliter and cubic centimeter are the same. And then we'll just use dimensional analysis here with this relationship. There are 1,000 milliunits per unit. There. So milliliters cancel, we just put liters. Here's a check here. A milliliter or cubic centimeter is very small. A liter is big, so we need fewer liters. If we went the opposite direction, that is, we move the decimal 3 the other way, we get 1 million liters. So that's our check. All right, now let's talk about significant figures. Significant figures deals with this, uncertainty. And with significant figures, not all these digits are uncertain. So if I had a length that's 1,892 or cubic centimeters, 1,000, oh, that's a volume, sorry. Is that a length? Well, let's just do this. Like this. Okay, is this for sure above 1 liter, this volume? Is this absolutely above 1 liter? So there's no uncertainty there, it's above 1 liter. Is this above 1.8 liters? Absolutely certain, there's no uncertainty, it's above 1.8. Is it above 1.89 liters? Yeah, it's definitely above 1.89 liters. Now, is it exactly 1.892 liters? This is where this becomes a little bit uncertain here. You know, is it right on 1.892 liters, or is it just a hair above or a hair below? You know, and it is just kind of close to 2. And so this, but these are certain digits here. And so there's no uncertainty associated with 1.89. The uncertainty comes in the 2. Now, how does it line up? And so when we express measurements like this, it's definitely more than 5 milligrams. It's definitely more than 5.2 milligrams. The uncertainty is it right on 5.25? No, it could be anywhere from 5.245 up to 5.254 milligrams. You know, all these would round to 5.25 times 10 to the 5th milligrams. Does that make sense? And so the uncertainty comes here, and this is why we have a little bit of range here. And so let's take a look at this in terms of measurement. Tomorrow's lab, we're going to do this. We're going to take measurements. And when we take measurements, we're only allowed to guess 1 digit. And that's called the uncertain digit. And it's always going to be the last digit written. The last digit written is your guesstimated digit or your uncertain digit. That's all this slide says. This, of course, does not apply to exact numbers. Exact numbers are by definition. Exact numbers are established by definition. So it's that 1 kilogram mass in France. That's exactly 1 kilogram. There's no uncertainty there because that's somebody defined as 1 kilogram. So let's say you know this bottom stick here is 1 meter. So this is a meter stick. How long is this piece of wood? is that piece of wood? Say maybe 0.5 is here. 0.6 is maybe here. Maybe it's 0.67, 3, 4 meters. How many guesses did I take? Am I guessing 0.6? Yeah, I'm guessing 0.6 because I'm just ballpark. It looks like 0.6. Okay, but I said 0.67. Well, if I say 0.67, I have two guesses. I'm guessing 0.6 and I'm guessing 0.07. So 0.67. That's two guesses. Am I allowed two guesses? No, I'm only allowed one guess. And so since I'm only allowed one guess, then the measurement is going to be 0.7 meters. You know, let's say that's closer to 0.7, so I'll just say 0.7. And so this is my guesstimated digit here, my uncertain. But what's uncertain about it? It's not completely uncertain. You know, as long as I can eyeball it pretty good. If I can eyeball it pretty good, then the error associated with that could be smaller. Normally the maximum error, which this is here, is taken as half. And so if it's taken as half, then this could mean 0.7, anywhere between 0.65 and 0.74. Anywhere between 0.65 and 0.74 will be about 0.7, right? But what they're doing is they're doing a little bit bigger maximum error. So this becomes anywhere from 0.6 to 0.8. Do you think that could hit to 0.8? Does that look like 0.8 of the weight? And so I think this is an overestimate of the maximum error. It should be about half the smallest digit. And half the smallest digit is usually what we do. The smallest digit is 0.1, therefore it should be half of that, 0.05, so it should be plus or minus 0.05. That's what I've been doing all along. Remember sterling silver? Sterling silver is 92, which means, you know, 92 plus or minus 0.5, which brings it to about 91.5 to 91.4, you know, something like that. Same thing here, take half the smallest would be 0.01. Well, what if we use this meter stick instead? If we use this meter stick, then there's less guessing here. Do we have to guess 0.6? No, but was it 0.7? Not quite to 0.7. So for sure it's 0.6. There's no uncertainty there. But the uncertainty is going to come from guessing how much farther is it from 0.6. So this looks like 60, is it 63 or 64? Isn't it? 63. So the 63 or 64 is the guess, the last digit. And so here they're doing 0.64 or 64 centimeters. And so if it's 64 centimeters, then what we typically do is we'll take half of the smallest increment, which would be 1. And so the plus or minus 0.5. And so this would be between 63.5 and 64.4, roughly, which seems pretty good. I think we can eyeball it better than this. They're doing. And I think they're overestimating the error. Let's take a look at this. Now, if I spend a little bit more money, I could get a more, what would you call this? You know, compare this meter stick to the previous one. The previous one were marked in 10 centimeter increments. This meter stick is marked in 1 centimeter increments here. And so what we say is that this meter stick is a higher precision meter stick than this meter stick. This is a lower precision meter stick, higher precision meter stick. What precision is how tightly we can narrow down that range, you know, the range of uncertainty. The more tightly we can narrow down that range, you know, the higher the precision. The wider the range, the lower the precision in terms of uncertainty. And so this one is going to have a much tighter range because here, do we have to guess 60? No. Do we have to guess 61, 62, 63, 64? Do we have to guess 64? No, absolutely. 64 is definite. What we have to do is we have to guess how much past 64 is it. And so how much past 64 is it? what I do is I divide this up into 10 imaginary lines. So I have a 5 here, and then let's go 1, 2, 3, 4, 5. And so it looks like it's 64.2. And so that's what they got here. 64.3 or 64.2 are good estimates. So they're guessing 2 or 3. And this is going to be much more precise because in the previous one we did point 0.5, but in this one we're doing 0.05. And so this is again a little overestimate. I take this divided by 2. So I have 64. This would range from maybe about 64.15 to about 64.224 or something like that. It seems tight enough. And so we're becoming more and more precise. Let's see if there's another one here. Yeah, there's another one here. This is a much higher precision one because now, do we have to guess 64.2? No. In fact, I see 64.2 is wrong. You see the 64.2 lines here and it doesn't quite reach it. This looks like definitely 64. Can you see? It's kind of hard to see. But it definitely looks like it's bigger than 64.1, smaller than 64.2. And so 64.1 is certain. There's no uncertainty. It's just how much past 64.1 is it? It looks like it's almost at 64.2, so I would say it's like 64.18, you say? Do you agree with that? 64.18? And so do you see how we're becoming more and more precise? You know, the higher the precision instrument, the more and more precise we are, which means the uncertainty spread, the uncertainty range is getting very, very tight. And so this one's 64.18 plus or minus what? Half of the smallest. So if this is 64.18 centimeters, I would say plus or minus, well, the smallest increment is 0.01. Take half of that, that would be 0.005 centimeters. And so that means the range is between 64.175 to about 64.184. I don't bring this to a full 5 because then it would round up. You know, so just keep it like that. Centimeters. And so it's becoming much, much more precise. You take a look at this measurement, 64.3. Where did they get that? 64.3. Does that match that? Not at all. So this is some kind of typo in PowerPoint. So this is completely wrong, the answer. And so it's an error in the typo and PowerPoint. So we're going to be taking measurements. When we take measurements, we got to make sure that we record the correct number of digits, the correct number of sig figs. Now, when we take measurements like this, we always worry about precision. The more precise we are, the better. But there's something called accuracy, too. And accuracy isn't the same thing as precision. And so we have to look at both accuracy and precision. And so what is accuracy? Accuracy has to do with, is the operator using this correctly? So for example, let's say we don't know what's on the end here, but let's say the ends were misaligned. You know, this was sticking in or sticking out from the edge of the meter stick. If we're sticking in or sticking out, then obviously, even though this is a very precise measurement, it's going to be wrong. And so if I'm trying to measure this, let's say I'm trying to measure the length of this marker, and I have it like this, and I'm using a very precise instrument, well, I have a bunch of marker hanging out here, right? It's not properly aligned. And so the user could be misusing the instrument, which means regardless of how precise it is, it's going to give you an inaccurate answer. And accuracy is how close you are to the real or true value, or the true length in this case. The other thing is wood. I mean, take a look at my meter stick. Can you see it's warped and bent? Do you see that? There's a curve here. Maybe it's hard to see, but can you see it's not straight and flat? Like this edge is up or that edge is, you know? And so what happens is this. I don't know if you, like old houses, you know, sometimes it depends on the humidity. Sometimes the doors are hard to open or close. Have you ever had that happen? Because of the humidity, the door expands and contracts. Well, if this thing expands and contracts, although this is dry, but if it expands and contracts, are you going to have an accurate measurement? No, not necessarily. And so accuracy depends on two things. It depends on user error, you know, and calibration. Now, these are cheap, right? These aren't very expensive. The same thing with our thermometers. If you take two thermometers in our laboratory and put them in the same liquid in the same cup or beaker, you'll get two different measurements of temperature. Which one's accurate? Which one's right? We don't know, because those thermometers are cheap, mass-produced units. If we want a really accurate thermometer, what we have to do is we have to buy a good quality one and then do something called calibration. Calibration is to make sure it's measuring correctly. And so, two things we think about when we take measurements, precision and accuracy. Now, the number of sig figs, does this tell me anything about the accuracy? Let's say I have 3 sig figs versus 4 sig figs. Is 4 sig figs more accurate than 3 sig figs?
Yes.
Well, it depends. It depends, because maybe the higher precision one was miscalibrated. Maybe when they printed the lines, they were all off a little bit. You know, there are a whole bunch of factors. And so sometimes it's not. But in general, we think of the association. In general, we think higher precision, usually a more expensive instrument, and usually more accurate. And so in general, yes, we typically think of higher precision, more sig figs as being more accurate. But that could easily not be the case because of improper calibration. And so the number of sig figs, the correct answer is no, false. The more sig figs does not indicate more accuracy. More sig figs indicates what? More precision. Well, since accuracy is in our control, you know, all we have to do is make sure we're reading it correctly, number one, and make sure that the instrument's calibrated. It's like, it's common, you know, if I measure the height of, let's say, this box of matches, you know, I could be very precise. That is, each time I measure it, I get the same amount. But I could be inaccurate because each time I measure, I'm looking down at it, or I'm looking up. If you're looking up at it or looking down, you're going to get a different number. You have to be perpendicular to it to get the correct number. And so anyway, that we can control. Just learn proper technique. Proper technique is reading it correctly and calibrating it. The precision, though, is something that, you know, in the way we can control, depends on the instrument we use. But normally it's just given. So here, how many sig figs is this? 3. The zeros don't count in front of the decimal. fact, some people don't even write the 0 here. They just write decimal, 000. How many sig figs here? 5? Okay, these zeros are not significant either. These are what we call placeholders, because if you wrote this in scientific notation, what would it be? 2.5 times 10 to the negative 4. If it's 2.5, that's only 2 digits. So it's 2 sig figs. What happened to these 3 zeros? Well, those are placeholders. So those disappear. And so those are not significant. The 3 and 2 is the correct number of sig figs. 3 sig figs for the first one, 2 sig figs for the second one. Sometimes we have to do rounding. This is a rule for rounding. If the drop digit is less than 5, then we don't do anything. If the drop digit is 5 or greater, then we round up. And so let's say we drop the 2. If we drop the 2, do we leave the 5 alone or raise it? If we drop the 2, do we do anything to the 5? No. Okay, let's say we drop the 5. If we drop the 5, do we do anything to the 7? Yeah, 5 means we round up, so the 7 turns into 8. If we drop the 7, then the 2 turns into 3. If we drop the 2, then 4 is the same. If we drop the 4, it's 1 stays the same. Can we do this? Can I do domino rounding? So for example, the 5 changes this to an 8. 8 changes this to a 3. 3 doesn't do anything for that, does it? Or is it okay to do that? Let's see, maybe this is not the best example here. And the answer is no. And so we only, in other words, we're only allowed 1 rounding step per calculation. We don't want to do multiple rounding steps in a calculation. Let's say you're calculating the annual interest you earn in some kind of savings account. And so you calculate the daily interest that you get. And so let's say your bank is supposed to give you 1.4 cents per day of interest, right? If you earn well, you can't have 4/10 of a penny, can you? And so the bank just says, well, since there's no 4/10 of a penny, we'll just round it to 1 penny per day. And then you have 365 days. And so you'll earn $3.65. Okay, that's called intermediate rounding. But really you're supposed to get 1.4 cents per day. And so what would be better is to do this. It'd be 1.4 cents per day times 365 and then round it at the end. You do 1 rounding step versus multiple rounding steps. Which one's going to be more accurate in terms of calculating your interest? Yeah, and so what this is this is called round off error. You know, the more rounding you do, the more error you introduce into your calculation. So we try to minimize that. One way of minimizing that sometimes is that I carry extra digits. So let's say there's no such thing as 4/10. So I would just do this, 1.4 cents, and carry that, and then round it at the very end. That's what I do. All right, now we're going to talk about uncertainty in calculations when we do calculations. And so we're looking at the rules for significant figures in calculations. These are rules, these aren't laws. So there's a, what's the difference between a rule and a law?
There's exceptions to the rule.
Yeah, there are a lot of exceptions to the rule. We wouldn't expect that for the law. And so when we look at these numbers, these are recorded using different precision balances. Balances measure bands. And so this balance here compared to this balance here, which one's more precise? This one came out to 319.5 grams. This came out to 20.460 grams. Which one is more precise? Yeah, 20.460. Do you see the uncertainty there is at the, not the 10th of a gram, not the 100th of a gram, but the 1,000th of a gram. And so we're looking at half that, so it's a very tight range. Whereas this one, we're just looking at the uncertainty as being at the 10th of a gram, which means it's going to be a much wider range. And so even though we're using a fancy balance here, it's not going to make any difference if we add these two up, because if I take 5 plus 4, where's the uncertainty going to be? If 4 is certain, but 5 is uncertain, then 9 is going to be uncertain. And so what we do is this. For addition and subtraction, the way we deal with uncertainty is this. If there's uncertainty in the 10th place, it's going to carry all the way down, no matter how precise everything else is. And so that means our final answer is going to have uncertainty in the 10th place, so we shouldn't go beyond the 10th place. We're only allowed one uncertain digit, the guess digit. And so this is why it was rounded to the 10th place. They didn't carry it further, because that's where the uncertainty started. That's for addition and subtraction. For multiplication and division, it's a different rule. For multiplication and division, it depends on how many sig figs we have, not how many decimal places we have. And so here, if I look at 0.0573, how many sig figs is that? 3. This is 4. This is 1.000 is how many sig figs? 4. This is 4. So I have 3 sig figs, 4 sig figs, 4 sig figs. My final answer can only have 3 sig figs. That's a rule. And so for addition and subtraction, we look at the smallest number of sig figs. That's what's going to dictate how many. For division, for multiplication and division, that's it. For addition and subtraction, it's the decimal places that guide it. And so we have to round this. So how do we round this? Do we do a domino rounding like this? 8 turns this to 3, which leaves that at 8, which changes this to, well, no, we don't do it. We just do one rounding step. So if we're allowed 3 sig figs, we're going to carry these. That means the 8 2 8's drop. We look at the first drop digit, which is 8. If the first drop digit's 8, then that's going to bump this up to 3. So we end up with 0.0823 grams as far as sig fig rules go. Okay, let's stop here for 10 minutes or so. We'll take a break and then start again.